Okay, hi and welcome to video notes on domain and range. Remember, this is the heart of algebra here, stuff that will carry throughout the whole year. Our focus then with domain and range, and the easiest way to say it is by the title, where's the function at? I know there's a song that probably mimics that, but we're talking about where the function's at. So we're looking to see if we can describe where we can find this function, both horizontally, how far left and right it can be, and then how far up and down vertically. And that depends on the function. So that's what domain and range are. Domain then is going to help us identify where the x coordinates are, or the inputs if we remember them from the vending machine, and the values that go into the function. The range then is going to be our set of y coordinates or our outputs, and we're going to group them together. Okay, so again, domain is how far left and right this function exists. So we have to find the leftmost point on the x coordinate, or on the x-axis that we can find, and it's right, and that's what we list for its domain. For the range, it's how far up and down. We like to do this sequentially, so I should have probably written this down and up, and left and right is fine for that one. We want to do the lowest value on the left and the highest value on the right. So before we start finding these points of low and high, we need to talk about that there's two types of functions that we're working with on here. The first one we've seen a little bit of already, which is what we call a discrete function. Now, a discrete function sounds really fancy for meaning that it's just points, or a set of numbers. So what would it look like? It'd look like a point, and then however many points are in that set. So it's going to be definite points. That'll make a little more sense when we talk about continuous, but they're going to be points that you pick your pencil up and set them down and make these points. And they won't be all in a straight line, of course, but I'm trying to demonstrate what they'll look like. Where a continuous function are going to be what we refer to as lines or curves. So we approach those a little bit different from the points. If it's continuous, you'll notice that it's a line. So that means all the points in between, so it's an infinite amount of points, where this is a definite set number of points. It can be a whole bunch, it could be a few, it doesn't matter. This is infinite. Every time that we draw on this is a line. So and the lines can look like any function at all, but if you don't pick your pencil up, then if you can do this without picking your pencil up, then you know it's continuous. If you have to pick your pencil up, it's a discrete. So let's take a look at what it looks like, how we define the domains for them, because it's both a little bit tricky. For this one, we're just looking at all the x coordinates for a discrete function. But with the continuous, we have to find the leftmost point for the x coordinate and then talk about all the possible locations it can be to the rightmost point. So that one's a little bit different. So let's take a look at how we would do that. If we're talking a discrete function, so sets of points, right, we're going to use what we call set notation to describe the domain, meaning that we're going to group all the x coordinates and then make a list of them from smallest to greatest in that particular order. And then we're going to do the same thing for all the ranges, again from smallest to greatest. Again, that's for discrete or actual points where you plot them. And again, they can be everywhere. Okay? Now, for continuous functions that are lines or curves or parabolas or exponentials, right, whatever those are, if we can't pick up our pencil and we draw the whole line, we're going to have to identify the leftmost point and its rightmost point, and then use what we call bracket notation to identify that. So we say, for example, whatever this point is here, we'd write it here for the x-coordinate, and whatever the x-coordinate for this one is, we'd write here. And this would say all the points in between. That's why we use this notation versus this notation. This means just these specific points, right? Just the specific dots. But this one's going to indicate all the possible infinite amount of points, and I don't know if you can see those tiny little dots I'm making there, every infinite number of points that can connect that line. Okay, so let's talk a little bit more about that. We know that there are closed, and you should have some prior experience, closed points, which means that they're included. We probably know that from previous experience. Those are going to be represented by square brackets. So if the end point is included, and that'll make more sense when you do an example, then it's going to be a square bracket. If it's open circle, meaning that point isn't included, okay, then we're going to use rounded brackets, and that's odd because it almost looks like a point, but it's not. Like, if I can spell that, point. Not though, okay? This time when we're talking about it, we'll define it as, again, domain and range. So when we say that, it might look like a point, but it definitely is not, okay? So again, just to review what that'll be is we'll find the smallest x-coordinate, and we'll write it on the left, and then square a round bracket, and then the largest x coordinate that we can find for this function, and we'll write it on the right, again, rounded or square. Range then will be the smallest y coordinate, rounded or square, and the largest y coordinate on the right, rounded or squared, based off if it's included or not. All right, so that's the notes for this section. I'm actually going to leave it there because we've reviewed how to find domain and range for both discrete and continuous points and drawn lines. And we know that the x coordinates refer to the domain, and that's how we identify it, and y coordinates refer to range. And the next video will be all the examples to go with it.